but one of the most pressing things, one of the reasons why I wanted to bring you in, because you are very knowledgeable in all things space, is the James Webb Telescope and all the different stuff that they've been finding, particularly about these galaxies that were formed very shortly after, not within our lifetime shortly, but cosmologically shortly after the Big Bang, that it seems like we have to figure out why these things are forming. Is the universe older? There's all this different kind of speculation. Maybe the Big Bang is not 13 point whatever billion years old, but maybe 22, 24. Like, what is your take on all this?
Yeah, the James Webb Space Telescope is such an incredible instrument. The data has just blown us away. You know, when you build this thing and you look at it unfolding in space, you think there's so many ways it could go wrong that we all were just like, you know, this thing was 215 moving parts or something had to unfold. So, you know, just the fact the fact it just all worked was just remarkable.
Right.
And then when we got those first images, they just kind of blew us away as well, because we had sort of these engineering expectations of what it would do, but the data was just even better than that. So when it, you know, of course, the first thing you want to do is point it to the most distant part of the universe and see what's out there in those darkest patches. And so when it did that, it started finding a couple of things. It started finding quasars, which is kind of the center of these very active galaxies. These are supermassive black holes that have loads of crap falling in, and they're spewing out all this energy. They're kind of feeding supermassive black holes. And so we started detecting those way earlier than we thought the universe should be able to build them. Because to make a supermassive black hole, I mean, these things are like 100 million solar masses. Imagine that, 100 million suns have not only been born but died, gone through their entire life cycle, died, collapsed into a black hole, and then those black holes have presumably somehow merged together into this super behemoth of this 100 million solar mass thing. So we're finding those just, 300 million years after the Big Bang. And that was like, hold on, that doesn't make any sense. Like, how can this be?
James Webb Telescope.
There's been a lot of media reports suggesting that the findings of the James Webb Telescope have undermined the case for the Big Bang. But there's an interesting backstory on this. Most of these media reports were based on the writings of a single physics researcher named Eric Lerner, who's been, since 1990, kind of carrying a torch to refute the Big Bang. One of his articles quoted a University of Kansas astrophysicist saying that she stays up late at night wondering if, based on the James Webb, that everything that we know is turning out to be false. Turns out that researcher, that astrophysicist, disclaimed his use of the quote, explaining that he took it completely out of context. That she was talking about theories of galaxy formation, not about whether or not there had been a Big Bang, and not about whether or not the universe is expanding as we would expect.
So he's confirmation bias.
Yeah, and in a sense also taking somebody way out of context to make a point of his own. He misused the quotation
on purpose,
apparently. And there have been a number of leading astrophysicists. In fact, people who would like to know more about this, I'd recommend Brian Keating from University of California, San Diego. Great astrophysicist, has been writing about this. But here's the short story. I wrote an op-ed in the Daily Wired distilling some of this stuff. What the James Webb Telescope is able to do is to, in fact, what it was constructed to do, was to detect extremely long wavelength radiation, stuff that's outside the visible range. I call it uber redshifted. It's actually in the infrared range is the more accurate physics term. So it's looking for very long wavelength radiation coming from galaxies that are very, very far out there. Now, why would it be looking for that? Well, because if the universe is expanding as we would expect based on the Big Bang theory, then the radiation coming from things very, very far out in space and therefore very far back in time should be very stretched out, more stretched out than stuff that's closer at hand.
What has changed in terms of our understanding? The Webb has been in the million-mile orbit, or however far away it is, for how long now?
Well, it got there, and then we did some engineering. So I guess a year and a half. Yeah.
And what has changed in our understanding?
So that's been people's first question. And what I want to do is temper that to say something a little different. So, yes, we expect James Webb to make great discoveries. We expect that. But the first order of business is hardly ever, let's discover something new today. It's, here's something that we have limited understanding of. Let's improve on that. And in so doing, we deepen our understanding of how things work in the universe. That doesn't always involve overturning a previous idea or discovering something that nobody ordered. All right? That will happen. We fully expect that to happen. But we targeted parts of the sky initially because we know other telescopes have gone there before. And we're going to say, how can we further advance and deepen our understanding? One thing it's going to be able to do, and it has already done, we have, you know how many exoplanets there are? I don't know how many of your audience was born after 1995. How many 27-year-olds and younger?
Probably quite a few.
Quite a few, okay. So I will take this opportunity to knight them Generation Exoplanet. 1995 was the first exoplanet discovered, a planet orbiting another star. And I'll never forget that because it was my first time on national television. I was freshly minted as director of the Hayden Planetarium in New York City. And NBC sent New York City is the media news headquarters, right, of all the networks. So NBC sent an action cam. They interviewed me because of my title, not because they knew or gave a crap who I was. My title was director of the planetarium. And so I gave my best professorial reply. I said, well, the Doppler shift, this is how it's discovered and what we do and how we measure it. And I was describing the fact that when you discover these planets, you don't actually see the planet. You see the effect of the planet's gravity on the host star. And so if you watch the host star like jiggles, okay, just a little bit in response to the planet going back and forth around it. So you're measuring the star. So I motioned that like with my hips. And that evening on the evening news, that's all they showed was me jiggling my hips. I said, oh my gosh. Okay, that's how you're going to do this. Okay. You don't want me to be Professor Neil. You want me to be Soundbite Neil. All right, so from then on, I practiced my sound bites.
We were seeing these images, these galaxies, and you can date roughly how old they should be based off the redshift. So the universe is expanding. So therefore, if something is very far away from us and the universe is expanding, its light gets stretched more and more and more as it journeys over space. And so we can use that redshift to kind of date how old these things are. When we use those dates, we look at these images, again, they seem suspiciously too old. You really shouldn't be able to form these things that early on in the universe. And so that kind of puzzled us. I think for the galaxy thing, there was a bit of a resolution there. One of the resolutions is that we probably miscalculated how easy it is to form these galaxies in the first place. So we had these models for galaxy formation, we had these models for how stars should form, how quickly they should live, but it was all essentially calibrated on what we see around us, like right here in this part of the universe, in the local universe. And then we kind of realized that those same models probably need to be tweaked if you're going to apply them to the early universe, where the density is so much higher, the gas temperature is much hotter, everything's just completely different in the early universe. So when you kind of make those corrections, it actually looks like maybe it's actually possible to make those galaxies earlier than we thought. So I think the galaxy problem is a bit easier to explain. I think the quasar problem to me is more interesting. How do you get those supermassive black holes so early? There's a certain kind of maximum rate you can feed these things called the Eddington limit. And that's so if you throw mass into a black hole and so much energy is going in, some of it spews back out. And the energy which spews back out stops other stuff coming in. Right? So there's a maximum limit. You can't build a black hole faster, in principle, than this Eddington limit. And yet, when you do the calculation, these black holes must have been fed what we call super Eddington. So faster than Eddington. So something's wrong with our models, right? Either we've got the universe age wrong, which I think is possible, but I would say that's probably a much less likely solution, or we've got the astrophysics wrong.
The James Webb was constructed in hopes of detecting that type of radiation if it existed. It's not assuming that it necessarily would, but it would be a way of confirming the expansion of the universe has been going on for a very long time. And in order to do that, the NASA people created some amazing technology. They supercooled the detection technology, or the detection apparatus, to I think 5, 6, 7 degrees above absolute zero, so that the heat coming off of the instrument itself was not creating infrared that would interfere. And what they were in fact able to detect from these very ancient, very distant galaxies was super redshifted radiation, uber redshifted stuff out in the infrared. And we're able, on the basis of that, to synthesize images of these very, very distant remote galaxies. Now, the very fact that they were able to do that confirms that you have that what you would expect on the basis of the Big Bang Theory, that the amount of redshift that you would expect to be present if, in fact, the galaxies had been expanding throughout that vast stretch of time was, in fact, present and was detected. Now, that didn't get reported. The whole focus was on the fact that there were galaxies that were more mature, there were more of them early on than we would have expected based on our theories of galaxy formation. And so those are anomalies that need to be addressed and have not yet been explained, as I understand it. Maybe the astrophysicists have made more progress on that in even recent days. But the basic picture of an expanding universe outward from a beginning has not been undermined, but rather confirmed in a very dramatic way. I think it's a rather dramatic confirmation. There have been many others. The cosmic background radiation that was discovered in 1965, the COBE radiation that George Smoot discovered in the 90s. So there's been this pattern of confirming evidence of this basic picture of an expanding universe outward from the beginning in observational astronomy from the 20s right up till now. And so that, I think, gives us good reason to think best we can tell the universe had a beginning.
Can I pause you on that? What is the when she was discussing the formation of galaxies, what had thrown that into question? Like what was about the formation of galaxies that undermined previous ideas?
As I understand it, it's that there are more galaxies that formed earlier and are more mature than we would have expected, because they were able to look back to 13.6 billion years ago. They think the origin of the universe is about 13.8 billion years ago. So apparently galaxies were forming faster than we would have expected. And I think that's the anomaly that is on the table.
But is it possible that with further detection, we can, with new data, have a better understanding of what is actually going on rather than just saying it all points to this thing?
Yeah, it's always possible that we can change our minds on things because science is always provisional. But there are many stable theories that have persisted because of a preponderance of evidence that points to and continues to point to the same conclusion. And I think we've had 100 years now where we've had repeated new types of observations that point towards a beginning.
What they were taking into consideration is the possibility that the Big Bang may be incorrect and that the universe might be larger and older than we think.
So, I hesitate to ask what pages on the internet you hang out on.
It was a legit. It wasn't saying the universe is older. It's saying as more data and new information comes in, there is a distinct possibility that the Big Bang might just be it just might explain the reach of the technology and not the actual scale of the universe itself.
Okay, so the way to think about this is, and this is the way science has worked since basically the year 1600, where Galileo sort of starts codifying what people knew probably should be happening, but no one really did it in large scale. If you have an idea about something, then you test it multiple ways and get other people to test it. And if the tests give you consistent results, you have a new understanding of the universe. When that happens, that knowledge of the universe doesn't go away. It doesn't get undone. What happens typically is you have a deeper understanding of the universe in which that understanding gets embedded. And you realize that you only understood a small part of a larger whole. But the small parts you did understand, where you had multiple experiments that confirmed it, that doesn't change.
If we're using something like the James Webb Telescope, so we're getting a much deeper view of the universe, how limited is the James Webb in comparison to James Webb 2.0, 3.0? Like, are we going to have to continually revamp what our understanding of this process is?
Yes, we will. And that's
exciting.
That's what I love, right? That's
Isn't
what
that great?
scientists love. Every time we've built a telescope that is, 10 times more precise than the last thing, every time we've done that, we have been surprised. And so these early galaxies are a good example. The cosmological experiments that are going on now, one of the big surprises is this thing called the Hubble tension. Have you heard of that? Hubble tension? So Hubble tension is measuring the expansion rate of the universe. How fast are things flying apart? And you can do it two ways. You can use the cosmic microwave background. So that's the earliest radiation that we can detect. This is that stuff that's about 3 Kelvin warm. You can detect in the microwave. And this is the light which has traveled basically when the universe was 380,000 years old. It's that light, and we see it in all directions. That's how we know the Big Bang didn't happen in one place. It happened everywhere, because you just see this light coming in from all directions. And from studying that radiation, you can kind of get a model of the universe, and then you can calculate, using this model, how fast should the universe be expanding today if I run the clock forward. And you get a number. And then, if you do that same experiment but locally, you actually measure the stars. You measure the supernovae around us, these pulsating stars, and you actually measure how fast is stuff expanding, you get a different number. They don't line up. And so this is really weird. So somehow, something's wrong, right? Either our measurements of the local universe must be wrong in some way, or this model that we're using to calculate the whole history of the universe, something is wrong with that model. So this is a very famous growing problem in cosmology. It's now what we call a 5 sigma level. So that means the chance of this being random is just like 0, essentially. It's just this is a real effect. And now we just have to figure out who's wrong. Is it the observers or is it the theorists?
Wow. Where do you fall on this?
Yeah, it's hard. I swing between both ways. I'll talk to my cosmology colleagues, and they'll, depending on who I talk to, they'll convince me either way. So I think that's
disturbing that people are convinced. If these new telescopes keep showing us this new puzzle, it always bothers me when someone is like rigidly convinced.
Everyone has a certain pet theory, right? They're trying to push. We all have biases, right? Yeah. So
human beings.
Yeah. If you've spent, it's hard, right? If you've spent 20 years of your life, most of your academic career, studying this one thing, it's really hard to turn around and say, you know what, I screwed up. Right, that's 20 years of measurements, they were all wrong, and I have to eat humble pie.
We have top people working on trying to resolve this singularity problem. And in so doing, you get to some ideas that, well, maybe our Big Bang, because the Big Bang is not going to go away. All the data support this. So now I've got this Big Bang thing, okay? And, well, is this embedded in something bigger? Ooh. So when you put like quantum physics and general relativity and you try to come up with some bigger understanding, deeper understanding, string theorists have been all into this, you get a multiverse. We didn't pull that out of our ass. That came out of the equations. So how old is the multiverse? I don't know. It's definitely older than our universe because it birthed our universe, and it births other universes, and it births, the way the equations drive it, an infinity of universes. This is the idea that maybe there's a version of us in another where I'm bald and you got the afro but everything else is the same.
And also a version where everything's the same.
Where everything would be the same, yes.
Everything you've ever said has been said before exactly in the same order.
Correct. There's no reason to presume that everything in this universe isn't or hasn't already played out in the exact way in another one of these infinite universes.
And in an infinite number of different ways.
Correct. And so that is what comes out of the equations. So that makes the Big Bang a kind of a small part of a much larger whole. And so, we're ready for that.
This, like in particle physics, you've got the standard model, which includes like all the particles and the electron, the baryons, all this kind of stuff. And in cosmology, we have a similar kind of model. It's called lambda CDM. And so the lambda stands for dark energy, and the CDM is cold dark matter. So this is our standard model, and we have used it to explain so much stuff in the universe, Joe. We're talking about the cosmic microwave background, oscillations in the sky, these baryonic acoustic oscillations, the stretching of the universe, Cepheids. You can use it to explain so much stuff, and it works beautifully. It works down to like the 0.01% level. So if you say the universe age is wrong, you have to give that up. So maybe it is wrong, but if you give that up, you have to come up with a radical new idea, which can now explain all of this stuff at that same level of precision. The much more likely answer, in my book, is that astrophysics, like the gas swirling around, the plasma colliding with each other, that's just more complicated in my mind than the natural model of just the simple expansion of the universe, which actually is a fairly simple geometric model.
If there was ever a scientific innovation project worth every penny, it's James Webb Space Telescope. The project cost about $10 billion, $9.7 billion of that coming from the U.S., $810 million from the European Space Agency, and $160 million from the Canadian Space Agency. Despite its huge figures, NASA's James Webb Telescope has far exceeded expectations. With its state-of-the-art instruments like the 21-foot mirror and 18 honeycomb-shaped segments, the James Webb Space Telescope has never failed to reveal unimaginable parts of our universe ever since its launch. The long-range infrared sensors on the JWST are also an added advantage to its amazing performance, enabling it to peer into the deepest parts of the cosmos. But you see, more than just capturing deep parts of our cosmos in ridiculously high-quality resolutions, the most interesting part of this telescope is its versatility. In just 2-year working duration, the James Webb Telescope has been used for many feats, such as revealing hidden galaxies and galaxy clusters, studying distant stars and quasars, and even observing planets in our solar system. But now, James Webb Telescope has taken things a step further by unlocking one of the greatest mysteries of science: dark matter. The science community didn't plan this. They never expected the JWST could do it. But the JWST is full of surprises, and now it seems scientists have been ushered into a new realm of possibilities with this telescope. Dark matter is one substance that has driven scientists to the extreme in terms of research. This mysterious substance is the core reason behind multi-billion-dollar science projects like the Large Hadron Collider. We all know matter constitutes nearly everything we see in the universe. But you see, many experts have bet hugely on the existence of another kind of matter called dark matter. But what exactly is dark matter, and how did it come into existence? Dark matter is a mysterious substance that makes up about 27% of our universe. This mysterious substance cannot be seen. In fact, it has never been seen before, but scientists have detected its effects all around us and in the cosmos. The study of dark matter so far has been quite interesting. Unlike regular matter, which consists of atoms, dark matter is different. According to standard cosmological models, atoms are believed to make up only about 5% of the universe. Sometimes it's easy to confuse dark matter with dark energy. While the two may sound similar or the same, they are very different. Dark matter is a substance in the universe, but dark energy is a force. If you've heard about the theory of the universe's expansion, dark energy is the anti-gravity responsible for this expansion. Think of dark matter as the mysterious invisible matter that fills up vacancies in the universe, while dark energy is the invisible force constantly stretching out the universe. Scientists believe dark energy makes up about 68% of the universe. Like dark matter, dark energy is invisible, but its effects are very much observed in the universe. But dark matter isn't just invisible, though. One other unique property of this substance is that it doesn't emit, reflect, or absorb light. Even electromagnetic radiation like X-rays or radio waves is useless against dark matter. This is why it has been impossible for scientists to detect dark matter directly. So far, a majority of the observations in our universe have been all thanks to gravitational and electromagnetic instruments. These are instruments that aid in detecting gravitational waves as well as capturing electromagnetic radiation in telescopes. But dark matter doesn't play by those rules. One rule that dark matter does obey, however, is that it interacts with other aspects of our universe, like ordinary matter. Dark matter interacts with ordinary matter in our universe. Thanks to this interaction, we can detect its presence. Whenever this interaction takes place, it causes certain measurable gravitational effects in our universe. These effects are mostly noticed in large such as galaxies and galaxy clusters. Using these observable effects, scientists create near-accurate maps of dark matter distribution in the universe. So, even though there's no visual proof that dark matter exists, there's experimental proof that it does. Now you may wonder how something invisible could still be very active and influential in our universe. Well, however strange it may appear, the concept of dark matter isn't new to the scientific community. There have been years of research and discoveries in this direction. Dark matter concepts date back hundreds of years to the days of Newton. At that time, they discovered something unique called the dark nebulae. These were strange clouds of interstellar dust that happened to block the light from background stars. But it wasn't until the 1930s that the first true observations of what we now call dark matter were made by an astronomer named Fritz Zwicky. In 1993, Fritz made some observations of the Coma cluster, and it revealed that there was about 500 times more mass than what was calculated previously by the great astronomer Edwin Hubble. However, this extra mass was completely invisible. Initially, Fritz's observations were met with much skepticism by the scientific community, but later on, astronomers confirmed that they were true. Fritz was the first to bring the strange concept of dark matter to light, no pun intended, but at the time, the majority of the science community wasn't having it. Vera Rubin was the astronomer who managed to convince the science community of the existence of dark matter. Her research was done 30 years after Fritz's, and it was a major milestone. Vera Rubin discovered that the centers of galaxies rotated at the same speed as their extreme ends. Normally, following the laws of physics, the center part of a spinning object is supposed to rotate faster than the extreme ends since the rotational force originates from the center. Vera expected galaxies to follow this law, but they didn't, which prompted her to investigate further, and so she realized that the entire galaxy was merely the center of a much larger structure. This was why it could have a consistent rotational speed from its center to the edges. But Vera didn't stop there. She went ahead to reveal that the missing structure in galaxies, which Fritz had earlier spotted, was dark matter. And so, the dark matter concept was fully introduced by Vera Rubin. Of course, the concept was vehemently disputed by scientists, but later on, her observations were proven to be accurate. In honor of her exceptional work in establishing the existence of dark matter, one of the recent innovatory telescopes in Chile was named after her, the Vera C. Rubin Observatory. Despite the pioneering work of Vera Rubin and other contributing efforts from various astronomers over the years, scientists still don't know exactly what dark matter is made of or why it even exists. This frustration has led the science community to create several experimental projects like the Large Hadron Collider, LHC, at CERN. Projects like the LHC aim to recreate dark matter under a controlled environment so that it can be studied effectively. But so far, that approach has yet to yield any tangible results, so scientists are still banking on assets like the James Webb Space Telescope. You see, while James Webb Telescope may not be able to detect dark matter visually like the stars and galaxies we find in the cosmos, it can detect the effects of dark matter in the cosmos and allow scientists to conduct an up-close study. This seems like a roundabout method, but it's the best scientists have been able to come up with so far, given our current technological abilities. By using existing models to observe the dynamics of galaxies, astronomers can measure how much mass is in stars and galaxies to help determine how much dark matter is inside them. You see, many galaxies would not be able to exist and move as they do without dark matter. This is one of the primary evidence scientists look out for. The large amount of invisible mess dark matter contributes will always be noticeable in scientific measurements. Where the JWST comes into all this? Well, with James Webb Telescope, scientists can precisely take extremely sharp images, which can then be used for further research. Such research will reveal observable disturbances caused by gravitational lensing, pointing scientists to areas where the invisible mass, dark matter, is lurking. Gravitational lensing is a phenomenon whereby light beams pass through a large mass and get slightly deflected as the fabric of space-time is slightly curved by the mass. Einstein's general theory of relativity well described this phenomenon. Through high-quality imaging of distant galaxies, the JWST can detect their masses and determine what is missing or not observable. Any missing stuff that's detected is most likely to be dark matter. It is important to note that no other telescope or space observatory can substitute the James Webb Telescope for this all-important task. This is because only James Webb Telescope can produce sharp images, allowing even the smallest disturbances to be measured. Moreover, the James Webb Telescope is the only instrument we currently have that can peer very deep into space. This is a huge advantage and allows cosmologists to access many more background galaxies and investigate them for traces of dark matter. One of the biggest discoveries of the James Webb Telescope so far was the ancient galaxy clusters discovered in the dark part of the universe, where nothing was thought to exist. These galaxies were among the first to form, and the discovery sparked controversy in the scientific community. Many scientists were puzzled as to how such massive, well-defined structures could form so early in the dawn of the universe. It was as if James Webb Telescope was trying to dispute everything we thought we knew. Now, James Webb Telescope has done it again, birthing another discovery that makes us doubt everything we knew before. You see, while we may have earlier described dark matter as a kind of substance that can interact with other forms of matter through gravitational forces, we must not fail to mention that it can self-annihilate, thereby producing energy peculiar to certain frequencies. There's more. In a recent science research paper, this special ability of dark matter was studied in detail, and a shocking discovery concerning the James Webb Telescope was made. The paper reveals that certain unique detections from the James Webb Space Telescope are not actually galaxies, but something entirely different called supermassive dark stars. They are neutral space objects combining dark matter and regular matter, producing specific effects on telescopes and space observatories. These effects are visible from really far away, which is why James Webb Telescope captures them. As much as the name dark stars seems absurd and hypothetical, these objects do not go against our established laws of physics. Going by the explanations of modern physics, these stars contain a cluster or nucleus of dark matter in the center, surrounded by a lot of gas. So, though it may be unusual, it's nothing too extraordinary. These dark stars are suspected to be most of the weird things spotted in the James Webb Telescope's images that scientists had previously assumed to be galaxies. They are still hypothetical for now, but if these dark stars are confirmed, it could be the final piece of the puzzle we need to prove the existence of dark matter once and for all. This new research paper gave us some insight into these dark stars and their composition. As we said earlier, the dark matter in these stars can self-annihilate, producing energy in the process. However, even though there is a lot of dark matter inside these stars, they also contain quite a lot of gas found in regular stars, like hydrogen and helium. However, these gases don't typically behave the same way they would in typical stars like our Sun. You see, in regular stars like our Sun, gases like hydrogen and helium undergo nuclear reactions in the star's core, producing light, heat, and radiation. However, in the case of these dark stars, these gases react differently due to the huge chunk of dark matter in the middle. Dark matter exerts gravitational forces on nearby matter, and so the gravitational forces from nearby dark matter prevent the gases in these stars from achieving a state where they're dense enough to undergo nuclear fusion. In other words, the only thing the gases in these dark stars do is produce very large gas clouds. Although these gas clouds are quite large, they are low intensity, unable to create anything other than a large nebula. These dark matter stars produce light just like regular stars, but in this case, the light produced is not the result of nuclear fusion, and it has nothing to do with friction either. Rather, the light from dark stars is due to dark matter interaction close to the center. Dark stars produce a lot of heat and emissions due to self-annihilation. The self-annihilation of dark matter stars releases large amounts of heat and forces many other gases, such as hydrogen, to stay away from the star's core. This prevents the occurrence of several phenomena that we see in other stars, like aging, collapse, and supernovas. Overall, dark stars are unique and unlike stars in many ways. For instance, they are much larger than typical stars. However, they do not qualify to be called galaxies, as they are much smaller than galaxies. The gas clouds from these objects could be anywhere from 4 to 2,000 astronomical units in diameter. This is quite small compared to galaxies that measure at least 100,000 light-years across. For context, 1 light-year is about 63241 astronomical units. Hence, you would need to place about 3 million of the largest dark star gas clouds side by side to fill up one small galaxy. On observatories, these objects appear as a kind of a point source from faraway distances. They possess very high surface temperatures and very high luminosity because the dark matter annihilation results in lots of gamma rays and high-energy particles. This study connected many dots about these dark stars, starting with one strange galaxy the James Webb Telescope captured some time ago. This particular galaxy is believed to be the farthest ever, with a redshift of 13.2. However, one thing scientists noticed about this galaxy was its unusual overall brightness. At first, it was believed that it contained the so-called population 3 stars. Population 3 stars are comprised mainly of the primordial gases hydrogen and helium. They are believed to be the oldest stars, formed just shortly after the Big Bang. The discovery of this supposed galaxy seemed like it would give scientists a chance to study this rare type of star. But now, based on this new research paper, it turns out that they were dark matter stars after all. One thing this paper points out about dark stars is that they have a separate absorption spectrum, the helium-2 spectrum. This spectrum is absent in galaxies. However, it is present in dark stars because they contain a lot of hydrogen and helium around them, enabling the creation of two different absorption lines. The analysis from this paper suggests that this faraway galaxy possesses this property, which disqualifies it from being a galaxy. Moreover, luminosity is another factor. The luminosity from this dark star is equal to the luminosity of billions of suns. All this goes to show that this galaxy, and possibly other faraway galaxies spotted by James Webb Telescope, could be dark stars. The authors of this paper even suggest that we may actually discover more of these dark stars through further observations and using other telescopes. You see, as impressive as the James Webb Telescope may be, there are certain wavelengths it cannot operate at. For instance, 5 micrometer wavelengths. If a special kind of radio telescope is developed to explore these wavelengths, we could have more detailed images and potentially find more dark stars. For now, the JWST is observing galaxy evolution. Scientists can compare these observations to theories explaining dark matter's role in the universe. This will lead to a deeper understanding of the amount and nature of dark matter in galaxies. Moreover, remember that the JWST was primarily designed to see farther back in time, to the early universe. And so, by making these deep observations into space, scientists can use the JWST to study the role dark matter must have played in the early beginnings of the universe and its evolution. James Webb Telescope, which is currently equipped with enough fuel and infrastructure to last 20 years in space, may just be what we need to solve the mystery of dark matter once and for all. It resides in a permanent location in space and has a wide heat shield to protect its delicate parts, like infrared instruments, from heat and solar radiation. NASA had to ensure everything was right before the launch because they had only one shot. If anything went wrong, reaching the James Webb Telescope to conduct any repairs would be practically impossible. Refueling was also not an option. However, with the amount of propellant on board, scientists are convinced the JWST should last the proposed 2 decades. Although dark matter stars are bringing a new perspective to the mysterious concept of dark matter, there are also other ways scientists are using James Webb Telescope to explore this mysterious concept. Professor Matthew Walker of Carnegie Mellon University is the principal investigator of a program that will use JWST data to work on dark matter using the cold dark matter theory. This theory predicts that dark matter exists in small quantities inside certain clumps called halos. Matthew Walker and his team will apply this theory by looking for perturbations from these subgalactic dark matter halos on various fragile gravitational systems. Just so you know, the science community is working on another massive project, the Nancy Grace Roman Telescope. The project is expected to launch in 2027. This telescope will be capable of supporting a wide field view, and so it would be able to capture images of wide swaths of sky, even wider than the James Webb Telescope. This will make the work of dark matter observation even easier for scientists, as they would be able to straightway study the effects of dark matter on large structures or portions of the universe. If and when we finally get a clear, detailed image of dark stars, modern cosmology will be able to confirm to us, once and for all, that dark matter is definitely out there. With the current progress and innovative projects underway in the science community, it's only a matter of time before that dream becomes a reality. Thank you for watching another episode of Voyager. While you are here, click the video on your screen to see more mind-blowing videos like this one.